the two very important lines. In fact, those who are a little inclined towards research work can go ahead with this while reading. I'll share 2-3 papers. They can read it. It's very important that you should follow the content as well as the referred books as well as papers. The precision, as it is told, that precision affected only by random errors in the measuring process, and accuracy affected by precision as well as existence of unknown and systematic error. The reason why, because this is the question that I should put in right now. Why? In terms of the second one, which is the this line, the accuracy one, accuracy affected by precision as well as existence of unknown as well as systematic errors. So why we are now talking about the systematic error? Okay, so it's a good question that you should probably try to find the answer for it. If anyone knows, you can comment. See, the reason why it is said so, that now if in the case of accuracy, if the deviation from true value is seen in a particular direction and precision is okay, precision is not questionable, then obviously that deviation from the true value or from the expected value is obviously because of the systematic nature. Let us see just one or two example that would be much more clear. Just a minute. Yes. So you could see in this figure that this A case, the case A, which we are having in picture. So case A is representing high precision, no bias. Obviously, the bias word we are using. Let me just the bias word. Oh my God. The bias word we are using is for systematic error. Okay, so in the case of systematic error, it is represented in second example, which is case B, where you could see that there is a slight deviation of all the observations. The precision is not questionable here. The only question is about why it is deviating from in this direction is because there is a bias in that represents the systematic error. So B is example of high precision, large bias, and that leads to low accuracy. If your system is free from blunders, free from systematic errors, then chances are very less that deviation from true value occurs. It only occurs if if there is an undetected systematic error. You could not know the reason why this systematic error is occurring in the observation, and that's why your observation represented like that. So it is a good practice generally. Before moving ahead into the system of equations, you just look at your observation. And if you find any such deviation where your measurement precision is not questionable, then you should look for the region as bias. The third one, obviously, the low precision, no bias, and low accuracy. Why it is no bias? Because there is no particular trend in either direction, whether it is in this, or in the direction. So all observations are scattered in a uniform manner. Okay. Similarly, in the fourth case, we have a bias as well as case of low precision. It is highly unexpected in geoinformatics that you should work with such kind of observations. Okay. So in a case of bell-shaped curve, which we are talking that our observations are, our observation containing random errors are following the bell-shaped curve or Gaussian curve. The assumptions are always there. Assumptions are that systematic errors and blunders have been removed and only random errors are left. Sometimes this is a little confusion among your students that, sir, if systematic error is present, then still they will follow the bell-shaped curve? The answer is no. That is not a chance. You will have to remove those errors before applying the Gauss law of accidental errors or probability theory for answering various type of question. In fact, the probability distribution will not follow. Okay, so that is the one nature. In fact, I have given you one question in the last class that what is the region that probability that maybe more number of observation are coming inside the E50 criteria. Okay, and the answer is same, that probability is very high that your observation are containing such errors which because of which the observation are accumulated or repeatability of observation is there. Anyways, the assumption is, if you have any questions, you can put in what if in terms of query regarding this. Second is systematic errors cannot be removed from positional information unless some means exist for their detection, such as comparing this information against given control. So there is a highly likely chance, obviously, because this is part of content which is sometimes not in your control. So what will happen? You collected the observation and there is still the undetected systematic error. We call it undetected systematic error. So when you call it the undetected systematic error, then there is a chance that you have to apply certain rules, or you have to apply certain detection test, and generally for identifying such systematic errors or undetected systematic errors. You apply certain class of tests, and these tests are nothing but the statistical tests, which we discuss at a certain point of time when we discuss about the outlier detection or data snooping. We will discuss such type of test. So you have to little patient up till then. So the question is again same.
Sir, please zoom this slide.
Sorry?
Sir, please zoom the slides actually, sir. It is not visible from my end.
Are you following in the mobile? I'm sorry.
No, sir,
please.
laptop, sir. So,
well, then it should be visible. If it is in mobile, then there is a problem. But if you are following in the laptop, there should not be any problem. So, and obviously to mention the accuracy of the product, the uncertainty of the products is stated. Okay. So this is a little, I'm just zooming a bit. Is it okay now?
Sir, थोड़ा सा और sir.
बेटा फिर हम
yes, sir, yes, fine.
I have,
yes, it is fine, sir.
I have to write also, isn't it? So I should have little place for hand to place my hand also. Okay. So this I think with this little understanding of accuracy and precision, now it should be very much clear that what is your vision in terms of data collection and how your data should behave. It's very important. Okay, you need not to worry about too much at the beginning. You just need to follow the protocols of data collection, and standard protocols are available for any kind of domain, whether you are collecting data from total station, from GPS, from LiDAR, or any kind of device which you have, whether it is a digital level, theodolite, whatever it is, for any kind of applications. Okay. Then there is the measures based on Gaussian law. So there should be certain measure of existing random errors associated with estimated value to describe and express its degree of what should I call it, goodness, reliability, and repeatability. Okay, so your observations or set of observations should be reliable. Okay, and in fact, let me tell you, in the case of, I just forgot to mention in the previous slide, just wait for a little, that should appear on your screen. The test which I was telling you in the case of in the case of detecting the systematic error, there is a set of tests, and in fact this part of your hypothesis testing. Okay, we will discuss about hypothesis testing in detail when we discuss about the distributions. We will discuss about hypothesis testing, and in fact in hypothesis testing you will be in a position to detect the undetected systematic error in the system of observations. So measure should be in accepting or rejecting certain observations. Very important that here you need to see whether your observations are going to be accepted or rejected, and generally we follow certain threshold to reject the observation, and we will see that part also. Measure of errors is essentially a different set of measurements and hence accepting more precise one, isn't it? Because there are two bunch of data is available. Let's say this is your bunch of data, one bunch of data, and this is your one bunch of data. So obviously the data which is the data which is very much close will have very peak distribution, and the data which is very far from each other like that, this will have like this distribution. So obviously this is more precise. The more precise, that means sigma 1 is less than sigma 2. Now this is a very tricky kind of situation, and you should be able to understand it. If there is a peak, okay, then the index for dispersion, which is nothing but the standard deviation. Obviously the index for dispersion is the so-called the this standard deviation or variance, that should be less compared to the dispersion index of this one. So this one sigma 2 and this is your sigma 1. So obviously sigma 1 is less than sigma 2. That becomes the measure to select the precise set of observation. Okay, any questions? In practice, besides the word precision, one always hears the other two words, accuracy and uncertainty. Okay, how much uncertain about your observation, and that's how we went to discussing the probability of errors. Okay, so that is one index which one generally applies rather than asking about in this set of discussion which we had in previous class as well as in this class. What is more important is that you should be able to pick those lines, those statements which people are generally saying in terms of data, rather than saying whether your data is precise or not precise. People generally ask how much uncertainty is associated with your data set, isn't it? So this is a way of saying one thing in a two different statements. So if I ask you how much precise is your data set, you simply have certain index which you can represent. Okay, but at the same time, people will also ask how much uncertainty is associated with your data set. Okay, that would be given, the answer for this would be given by the probability theory. We have done in fact in the previous. Okay, then there is a term called absolute accuracy. Okay, so absolute accuracy has as meaning has same meaning as accuracy, and because absolute one, you have very certain about the protocols that are given or the standards that you have to follow for defining the accuracy. Okay, so that is how well does the measured quantity compares to the true quantity, and generally these absolute indexes are generally being given in terms of theoretical sense as well as in industry generally applies such kind of absolute accuracy kind of phenomena, because they have assembly lines where they have a set of distance which they have measured by several means and has given or assigned a best estimate of true value. So absolute accuracy is a theoretical word, but is generally followed in industry. You will see many templates where they will use this word called absolute accuracy. Absolute word will only come if you are very sure about the nature of the true value. Okay. So compared to the comparing data points on map, chart, or related products to points with known horizontal positions and elevations on the specified geodetic datum and mean sea level. Okay, so obviously, just like I mean, those who are with a different background, the benchmark word, there is a word called BM, which is, we call it benchmark, which is a very height of known, very well known uh, uh, above mean sea level of a point, that we call it as a benchmark. But following a loop and again going back to the benchmark, you may not get the exact, let's say 100 meter is the so-called benchmark height was there, and you have started a loop taking various observation in between multiple places, okay, and coming back to again this place, there would be a chance that you will not achieve the 100 meter, isn't it? So that is nothing but the loop closer. We will discuss that part in detail. But what we are doing, we are comparing uh, uh, data points on map, chart, or related products to points with known horizontal positions and elevation on the specified geodetic datum and mean sea level. Absolute error will include all uncertainties and bias associated with relating the product to the specified data. Similarly, if you talk about the absolute horizontal accuracy, so defense mapping agencies of US defines it as a statistical evolution of all random and systematic errors encountered in determining the horizontal position of a single data point with respect to a specified geodetic reference datum, and it is expressed as circular error at 90% probability level. Now there is a very new concept or new line which is coming up, which says circular error. So you have to wait a little for 5 slides. Then we'll discuss about the circular error. But at present, the horizontal word is a 2D word, isn't it? It is not a 1D word. Here you have X as well as you have a Y. In the case of absolute vertical accuracy, you have only one dimension, 1D, which is H. Are you clear or not? Because in the case of 2D nature, the error measures are a little changed compared to the one dimension. In one dimensional, you have linear error, okay, that we have discussed in the last class, where you have tried to identify various error levels, standard error, one sigma error, linear error, standard error, isn't it? So these kind of errors which you have done or have performed as an example in the previous class is an example of linear error. Okay. Okay. Apart from that, what we are discussing about the absolute nature of the accuracy, because here it is not precision, it is absolute accuracy. So what we are discussing here, we are discussing that what is the definition of absolute horizontal as well as vertical accuracy. So in the case of vertical one, we define as the statistical evaluation. Please remember the statistically evaluated distance of all random and systematic errors encountered in determining the elevation of a single data point with respect to mean sea level. It is expressed as linear error at the 90% probability level. Now, since you all are not very much aware about which I have discussed, because since it is talking about both random as well as systematic errors, so when you performed hypothesis testing, and generally it is given that the absolute vertical accuracy is this, okay, in a question, let's say it is given that vertical accuracy of this particular instrument is this at 90% probability. Maybe sometimes manufacturers firms are audited by defense agencies which are whole sole authority of giving a thumbs up nod to their instruments. Okay, so they generally perform such type of test when when they say that just like your certification of films, you have CFTI. Similarly, here in the case of Defense Mapping Agency is the authority which gives these kind of evaluation to the manufacturers who claim that their absolute horizontal and vertical position accuracy of points is this. So they generally perform those hypothesis tests, and while performing these hypothesis tests, they determine that at what level of probability that this value is treated as absolute vertical position. So we'll solve those problems. I hope you get the point. The reason is very simple, that in terms of absolute accuracy, what are the parameters which we have to define? Okay, any questions so far? You have a time, just see and try to find if you have any question. Okay, so moving ahead with your obviously the relative accuracy point, which is obviously after absolute. What is the opposite of absolute? You have the relative accuracy, which is slightly better, because you do not need any kind of I mean nod from any agency. Instead, you define it in a relative manner. So relative point to point horizontal accuracy, that is the statistical evaluation of random errors encountered in determining the horizontal position of one data point with respect to another. And it is expressed as circular error over a specified distance at 90% probability level. And relative point-to-point vertical accuracy, it is again the statistical evaluation of all random errors encountered in determining the elevation of one data point with respect to another. And it is expressed as a linear error over a specified distance at a 90% probability level. But what is point to be remembered here is that in the case of relative accuracy, you are not including the bias or systematic errors. Please remember, it is the statistical evaluation of all random errors encountered. Okay, so it is a relative one. And what are important to focus here is that relative accuracies do not translate into absolute accuracies. And you have certain examples for that. For instance, the relative accuracy involved in resolving a point on an image is not the absolute accuracy of positioning that point on the ground with respect to a geodetic data. Due to their nature, relative errors will be smaller than absolute errors. And if you compare map points to points positioned by field survey, which is on datum for which the absolute accuracy is desired. So generally you work with relative accuracy, it is safer to work with that. And you will see a lot of examples also in order to perform these tests on of statistical evaluation. Okay, coming back to the term called uncertainty, which is nothing but in addition to precision and accuracy, uncertainty is another word, another term used frequently to express reliability of the measurements. Okay, and it is the range or interval within which it is expected that the errors of measurement will fall, of course with a certain level of pre-specified probability. So the second statement which you say, the second statement apart from the precision which you follow, and this is the equivalent to the confidence level. that the uncertainty in my data set is from this to this. That is the range you are mentioning. And this is equivalent to the word confidence level with alpha percent probability. Okay. And for normally distributed observation, it is expressed in reference to the standard deviation of measurement. Okay. So I hope this is clear, because we have this, because now it is, I mean, we cannot spoon fed every time what you have to say, what you have to not. But the moment you try to follow the books, moment you try to follow the reference papers, these terms will be frequently used. And at that time, you cannot say that, oh, I do not know what is uncertainty. I forgot to read. I forgot to revise. So these kind of, I mean, you have to be responsible enough so that you know the technical content. Because in this field, if you do not know the basics, you cannot work, because the error will be that much that will affect the whole work. You have to be aware of the errors, the nature of the errors, the sources of the errors, as well as in what type of errors you are working, so that only when you can reliably, I mean, your observation would be reliable enough to defend any sort of hypothesis. Okay. There is another term which we call it as a mean square error, MSE. So how do you define the mean square error? Obviously, the word mean, when it comes mean, obviously you should have certain operator to define the mean. Obviously, at present, since we have not explained much about expectation operator, but please remember, expectation operator is one operator which returns the so-called mean. What is expected from this individual observation? It is expected that it should be the mean value. Okay, so this is just one way of representing the so-called expectation. So mean squared error of x, mean squared error of x is the expectation of the square of the difference of x and its true value. See, the value x and mu x. You could also call it mu x. Okay. And the dispersion which we are representing here, you could see dispersion, which is dx, is nothing but we are replacing mu by ex, because we know how we are representing mu by ex, and then it is nothing but we are going ahead with, you know, certain what should I say, the a minus b whole square kind of thing. Okay, so obviously there is one term which is missing out here, but anyways you will understand what it has represented, what is the uh, equation which is represented as expectation of x square minus mu square. Okay, why it is minus mu square? Because if you open it up, a square plus b square minus 2ab, that minus 2ab term becomes minus 2 mu square. You can work it out in your notebooks, but probably you will understand that minus 2 mu square and plus mu square will become minus mu square. That's how it is. Expectation of x square minus mu square and is equal to sigma square. You have to practice it, otherwise it will be very difficult to pick it up. Okay, that is the nature of mathematics. You cannot read it just like a botany or geology class. You have to do it from your hands. You have to write it. Okay. So a mean squared error can be expressed as a combination of dispersion plus a squared bias term. So you could see here that mean squared error is represented as, you could probably see from this equation that what we are trying to represent it in a sense, to combine, express a combination of dispersion, which is nothing but this one, and the so-called squared bias term. And when you write it, you probably could follow that expectation would be x minus ex square minus 2x minus ex mu minus ex plus mu minus ex square. The whole, if you open it up, it will become this one. there is no rocket science in that. It is just way of recombining a different term. Obviously, I mean, derivation is just to give you a little comfortableness. Otherwise, it's okay. You can quickly move ahead if you understand this part, how to write the mean, squared error, and dispersion. Okay. Since x is a random variable, but expectation of x is not. Why? बताइए. बता सकेंगे. अरे any guesses? I mean, you should attempt this question because it's very good question.
सर क्वेश्चन यही है जो लिखा हुआ है सिंस x is a random variable but ex is not.
Yes. Why?
सर
Sir,
क्वेश्चन बिकॉज सर
for all the
बताइए.
observations, mean will be of numerical value.
Yes, good. Because if your vector is like x1, x2, x3, this all x1, x2, x3, x4, all, but there will be only single mu x, isn't it? And that is what expected from individual observation. If you take expectation to x2, it would be the so-called this mu x, isn't it? So this is why expectation of x is not okay. So again, that mean squared error is represented by dispersion dx, or you could say dispersion operator. It's just like you have expectation operator, you have dispersion operator plus this bias term. This is beta square. So you can go through. I'll just upload the slide now. The content is covered almost. I'll upload the slide and you can go through and try to follow the content. We can have a discussion class in case you have a little problem with that. Okay. So now your bias term, which is your beta, is represented as very similarly the mean of the what is expected from one observation and how it is deviating from the actual mean. That is the bias. So the dispersion of x and mean squared error of x are not only equal in absence of bias, or in other words, only if needed mu is equal to your so-called ex. Very good. We will solve a lot of problems with this concept because in one chapter of I would think that the if you're following the Mikhail and Grisi book, I think the second chapter, which has content about introduction to errors, and in fact errors in the measurement, in the second chapter itself, if I'm not wrong, this very much concept is really used, where you are trying to work with the bias or the systematic nature of errors and how it is related and how it is going to be solved in case you are not going to dealt with the random errors, because random errors are dealt slightly different manner compared to the bias. So dispersion variance is an indicator of precision, and mean squared error is a measure of accuracy. It includes both dispersion and bias. Very good two lines. From here onwards, it would be beneficial that you should follow that, because I'm again repeating, because dispersion, which is an indicator of the variance, will be obviously dealing with the cases where your bias is absent. Bias is not in the picture, but when bias is there in the picture and you have to give the measure, then it would be relatively given by the mean squared error rather than the dispersion, because you have a bias in the picture, and it includes both dispersion as well as bias term. So it's very good two lines. and I think you should remember it, that what will happen if there are undetected systematic error in the system, how it will be better represented. Then it will be represented by mean squared error. And if there is no systematic bias or outlier, then obviously the dispersion would take over, and you could represent as an indicator of precision. Okay. So in general, it is harder to meet the accuracy standard than the precision standard. We can typically increase precision by making more observation, or in other words, we call it redundant observation. Redundancy. When we increase the redundancy, then increasing redundancy would help us in many ways, because it would help us in detecting outliers, it would help us in detecting biases, and a lot more. Because the moment your redundancy is improved, you have a lot more observation to deal with. Okay. Though this will come with additional cost in time and resource, because when you go into the field for data collection, you quickly want to come back to your office. You do not want to spend too much time. So, but at that time, you do not have too much in your hand. The moment your station is established, you have committed thousands of rupees to reach to the field. You obviously, to be more precise, just like we have done in our deformation monitoring surveys, at Uttarakhand, we try to repeat the observation. Suppose we have taken GPS measurement on day 1. When we go back, or day before coming back to our campus, we generally repeat those measurements, just to be make sure that in any case, whatever has happened on day 1 could not be the problem for data processing. Okay. So, however, it might not be possible to reduce bias by making more observation, because if it is there, it is undetected, you are not aware of it, it will always be there. And it may be very difficult to determine the origin of bias. So square root of mean squared error is commonly called as RMS. So we call it as root mean square error. And thus, strictly speaking, standard deviation and RMS are only equivalent in absence of bias. Very good line. I mean, this should be your basis of understanding from now onwards, that you have RMS, you have standard error. Both notations are different. Sometimes people simply say RMSE, simply call it RMSE. They do not represent it with any sign sigma or so, but they write it as RMSE. But the standard deviation, which has a very unique sign, as sigma. So this will prevail if random error is there. Okay, and this will prevail if random error is, obviously you cannot ignore in any observation, plus the bias. Any questions so far? So measures of precision. So obviously in your, I mean, with your PG background, now it is not the case that you will only have to deal with linear errors or single dimensional error. You have to discuss all three cases of single, 1D, 2D, and 3D, isn't it? So in your subject case, there may be a chance that variability is n-dimensional. We are just only discussing about 1 dimension, 2 dimension, 3 dimension, but the variability may occur in any dimension. It may be 1 dimension, it may be 2 dimension, and it may be 3 dimension. Okay. But obviously, since we are discussing the measures of precision, now we are minusing the bias. That means we are not including the bias term here. We are only describing the measures of precision, which is in with the help of sigma. It's very important. Okay.
Sir, here the meaning of dimension is number of variable. What, sir?
obviously the random variables associated in your observations, length, width, volume, everything is coming in same picture.
Okay, sir.
I mean, if you are working with only heights, let's say level network or high determination network, okay, you are only working with height differences. You are working with only one observable, that is height. But in your actual topographical mapping, you do not always work with height. You have to work with horizontal positions also. So automatically that becomes 2D. The moment you work in horizontal dimension. Obviously, sometimes what happened, the height network are differently dealt with. They are not generally combined with the horizontal network. And the reason is very simple, because the two different instruments have to be in picture. Although total station is a combined way of doing the data collection, but generally height network is generally work with digital level or lateral level kind of instrument. There is a different instrument that very well precisely give the height difference between 2 points. Okay, and obviously the horizontal position, you have to work with the 2 dimension, the x and y. And when you have 2 dimension, the dimension measures will also be changed. Suppose you are working with GPS kind of instrument where you have X, Y, Z, all three at the same place, plus the height network. So a point in GPS would have a Cartesian information Z, X, and Y, but at the same point, this point will be given a orthometric height by a different leveling network. Because ellipsoidal height from GPS, you will later on realize, maybe by in this semester or maybe next semester, the ellipsoidal height doesn't serve the purpose in terms of height estimation in a local continent. Okay. So that is the one example where you have to work with both 2D representation as well as 3D representation along with single dimensional observation, which is nothing but the height observation. Okay. Any questions? Okay. So one-dimensional error, which is again, it's very same we have discussed and we have solved these. In fact, the what should I say? The Gaussian distribution, and we have seen that for Gaussian distribution of a random variable, we have these equations. So I don't think any kind of problem here to look at this picture, that by Gaussian distribution curve of errors, we have mean, which is 0 and is identical in form of this observed value. My question again, why it is 0? बताइए. देखिए सभी लोग पार्टिसिपेट करेंगे तभी आपको बेहतर इसमें समझ में आएगा. एक या दो लोगों से काम नहीं चलेगा. Again, I am asking, for Gaussian distribution curve of errors, we have mean is equal to 0. Why?
सर क्योंकि हाफ ऑफ द वैल्यूज जो होती हैं सर वो मीन के नेगेटिव डायरेक्शन में होती है और हाफ ऑफ द वैल्यू पॉजिटिव डायरेक्शन में.
यार क्या बताया
हाँ
हमने
सर,
तुमको?
फॉलो बेल कर्व सर.
नो. बहुत सिंपल क्वेश्चन है, सीधे स्ट्रेट फॉरवर्ड इसका आंसर है. फिर से सोचिए, बताइए.
सर इक्वल प्रोबेबिलिटी होता है पॉजिटिव और नेगेटिव एरर होने का.
नो यार, नो नो नो. पारुल बताइए आप। देखिए ये होता है, I mean I am just going ahead and ahead with the slide. I do not have any competition. I do not have to finish it early. We'll have extra classes if we have to finish it something. But the only issue is that you should all follow the same. It should not be the case that one is following very, I mean, immensely, and another one is doing just okay, slide chal rahi and they just have mobile in their own hand and just they listening it as a some audio lectures. Parul, are you not there in the class?
Sir, I am, sir, because it follows bell curve, sir.
No. Again, just whenever
Sir,
a
in
question is asked about. Yes, Abhijit, yes.
Sir, in standard normal variable mean is 0.
No. There's no point of converting to standard normal distribution when you have straightforward answer. Give me just what I'm typing. Just you have to, again, whenever a question is asked about the mean, variance, anything, you just have to come back to backstage. What is expected from an error? What is the expectation of this error?
Deviation from expected is error.
No. Just look at this. First, look at this. What is expected from an individual error? Ideally, what is expected?
Sir, it should be 0.
To be minimum.
It should be 0. And then if it is expected that from error should be 0, on the left hand side, what is this represent in terms of statistical variable? This is nothing but mu ei.
Mu.
That's it. That's the answer. No positive, negative, no bell shape. Forget about everything. Just simply stick to the basic. The moment you are very equipped with writing those statements, then there is no problem. Clear? Question any? Then I think rest of the content is very easy. I said everything is discussed. Okay. So since the true value of a quantity cannot be measured, an infinite number of measurement is impractical. Estimated value obtained from a finite number of sample of measurement must be substituted for true value and the parameter of density function. What are the parameter of density function? Parul, बताइए. Question is clear? Am I audible? Hello?
Yes, sir.
बताइए भाई, what are the parameters of the density function? ऐसे कैसे हम आगे बढ़ें जब आप लोग इसी का आंसर नहीं दे पा रहे हैं?
Sir,
वो जो
mean
a
and
और b
standard
वाला आपने
deviation.
बताया था x minus a upon b minus a.
क्या x minus a upon b minus a? What is this?
सर वो जो डेंसिटी फंक्शन में जो हम लोग पैरामीटर्स यूज करते हैं चेंज करने के लिए, a और b हमने कांस्टेंट्स लिए थे जो.
क्या
if
ए और बी,
x
कहाँ चले गए तुम, कहाँ कहाँ चले गए तुम ए और बी लेकर के? थोड़ा अपने उसको ओपन करिए, विजन को. Stick to your basics. Do not follow any examples too much that you are just probably giving reasons from them. Abhijit was right. The
Sir, mean
parameters of a density function is mean
and
and
standard deviation.
variance. That's how you write, isn't it? You write as n, and then within bracket you write as mu comma sigma square. That is, mean and variance are the two parameters for representing a data set in bell-shaped curve. Any questions? See, the reason why I'm so particular about certain content of the slide, because that is where if you hit hard, if you ask right questions to yourself, that I'm aware of these questions or not, that is very practical approach to this course, and as well as for learning the content. Because what will happen as part of slides, you will have too much slide content from all possible courses what you are going through the semester. But what is important is whether you are picking it up the right content which is required to get the course outcome finally, because every course will have course objectives as well as course outcome that would lead to your program outcome. So it is expected that you will be more focused towards the basics content rather than following or remembering the too much theoretical basics. It is very much expected that you should be aware of the minimum required content which is there. And as an engineer, it is very much practical also. Okay, engineers work with a minimum threshold knowledge, and as and when required they change and learn at the time when what is required. But there should be some minimum threshold without which you cannot start it. So it is also expected from you. Anyways, the second line says that what should be the minimum number of samples? The answer is 30. Now there is a practical reason that this 30 value has been arrived. The reason is very simple, that there are two types of distribution there in this statistical theory. One is, we call it normal distribution or Gaussian distribution, and there is other distribution which we call it T distribution. Anyone aware of this T distribution? This T distribution is very simple. When you do not have large set of observations, so any observation less than 30, it will follow the T distribution. And this T distribution also represent, I would not say the exact bell shape, but a smooth bell shaped curve for less than 30. And you have a table to follow from where you will give the answers for questions asked related to dispersion, mean, and so on. But obviously the objective was simple, that if you do not have access to large number of population or data for estimating the mean and variance, you can work with minimum sample or minimum data, and that is expected that you should have at least minimum 30 such observation. Okay. Okay, coming back to most probable X bar, which approximate the true value and is determined from the arithmetic mean of observed value. It's very simple. Similarly, the true error is approximated by residual, which is defined as the difference between the most probable value and the observed value. I hope it is very clear because it is just a revision. Thus, please remember the residual word is very important. You cannot say, you cannot represent it with any other such errors. Okay, it is properly called as residual. Okay. The standard deviation from a sample, also referred as a standard error, is represented by this equation. So when you have your x bar as summation of I to 1 to n xi divided by n, or like this. Now my another question is, why these calculated by this function only? Why the expectation operator of xi is given mu x or x bar, and expectation of xi minus mu square is given as sigma x square? Why? Why there are not any other value compared to this? कभी आपके thoughts में आया question ये कि नहीं आया? I'm again repeating what I'm trying to ask you is, why it is expected that the expectation of observation xi will approach x bar? Why not something else? Why the expectation of deviation from mean of an individual observation and square of it will approach the variance or sigma x square? Why not something else? Because dispersion measures are explained in your basic statistics, as well as mean and what you call it, the representation of the so-called mean, median, mode. They all are representation of the different representation where you actually try to depict the picture. But why it is expected, or what is the expected value from the individual observation that it would reach the mean, or it would be the mean? Because this is a question that you should that has been statistically solved, and when it is statistically solved, the answer arrived as mean. That's why this mean we are using. That's why the variance we are using. We are not using any other representation, isn't it? Because one could also argue that expectation of xi should also be median of all observation or mode of all observation. Why is it not so? कोई जवाब है अभी आपके पास?
Sir, 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 the expected value is always defined in term of a weighted average of whole data set. So that is the reason we are considering mean mu.
No, that is okay. Expectation definition, if you go by expectation definition, is represented by integral minus infinity to infinity x and px, isn't it? Oh, that is okay. But why it is reaching to this mean and your so-called
सर जिस इवेंट
what
की
should I say, the variance?
हेलो सर, सर जिस इवेंट
हाँ,
की
I'm listening. Just
सर रिलेटिव प्रोबेबिलिटी सबसे फ्रीक्वेंसी सबसे ज्यादा होगी, उसी की तो चांस होगी अकरेंस की.
Say again what you are trying to say.
So the relative frequency of an event, the more the relative frequency, that is why.
नहीं नहीं नहीं, इसको statistically prove करेंगे, अभी नहीं, just wait for a few lectures, we will statistically prove and mathematically derivation हम देंगे इसका कि why there is a reason for that. Okay, anyways, this is the right moment to pose this question because you should be aware that there is a possibility to answer it. Okay, so normal PDF of errors, we again represented by, by the same equation which we have discussed. The parameter x bar and sigma x may assume different values as various samples are selected from same population, and therefore random variables with dispersion expressed by similar parameters. Okay. So standard deviation of mean and standard deviation of the so-called I mean standard deviation of the mean. I'm just trying to say. So this is the standard deviation of the mean. This is a very different index which is written as. This is different. I'm just again zooming it up a bit so that those who are following, they may try to see that sigma x bar, we are requesting that what should be the standard error of mean rather than a standard error of the observation. We are asking here standard error of mean, and you can prove it after few lectures when we discuss about the error propagation. You can prove it that this value is nothing but sigma x by root n. At this moment, maybe with your background knowledge, some of you could prove it, but later on you will realize that you can prove this out. And standard deviation of the standard deviation is this. So we are, asking two questions: standard deviation of mean and standard deviation of standard deviation. अब कोई बताएगा ऐसा क्यों हम स्टैंडर्ड डेविएशन ऑफ मीन और स्टैंडर्ड डेविएशन ऑफ स्टैंडर्ड डेविएशन क्यों पढ़ रहे हैं? क्या नेसेसिटी है इसकी?
डिस्पर्शन देखिए.
But please focus on the question first. Do not jump to conclusion. The beauty lies in the question itself. What I'm asking is, ask the standard deviation of mean. Previously we told we have mean as a single quantity. Dispersion will only appear if you have, complete the sentence. Dispersion will only appear if you have बताइए, कंप्लीट नहीं कर रहे हैं आप लोग, स्टेटमेंट कंप्लीट करिए. Dispersion. Yes, you are right. Dispersion will only happen if you have large number of such observations. Then only dispersion will happen. But mean will have only one value. Then how come there will be a distribution? There will be a dispersion. And if mean is only one, then how come you are representing it by standard deviation? क्वेश्चन आपको समझ में आया एवरीवन? भाई थोड़ा रिस्पांस दीजिए कि क्वेश्चन समझ में आया कि नहीं आया?
यस सर.
अभिजीत बताइए, what we are asking here.
सर आवाज नहीं आ रही थी, बहुत कट कट के आ रही थी।
भाई नेटवर्क आपका ठीक नहीं है क्या? हमारा तो ठीक है। My question is same, that we are talking here about standard deviation of mean and standard deviation of standard deviation. But in general, when you have when we are talking about the mean, we generally have a single value, isn't it? Then why we are talking about dispersion here? Why we are representing it by standard deviation? Now it is audible, Abhijit?
Yes, sir.
बताइए। भगत, आप बताइए।
So, to estimate the mean with great precision.
No. First, you have to pick the origin point of this question. Shubham, Valley Shetty. Okay, I guess you could not pick the question. Just come back to previous slide. See here, the last line. इसीलिए कहते हैं स्लाइड पे फोकस रखिए। स्लाइड पे आपका फोकस घटा और क्वेश्चन में आ गया, and you could not able to identify the last line. Please, everyone, focus on it. The parameter x bar, the word we are calling it as a parameter. Parameter may have multiple values, but when these parameters will have multiple values, they will not have multiple values in the case of population. They will have multiple values when we talk about the samples, because from population you are drawing multiple samples. So let's say from a population 10 samples have been drawn, so there would be 10 variances, 10 mean. That would be considered as an estimate of the population mean and variance, isn't it? You jump to 10 means, and at that time only it is said that you know, so when you have such set of samples, then only you would be posing this question which we are interested in, and that's why these two are the quantities which are there. Now I hope it is very much clear. That is why I'm saying that, because these are very small, I mean, set of doubts which will remain if you do not follow the basics. Initially, when you are working with population, so working with the population will have single mean and variance, but working with samples, you are working with too many mean, x1 bar, x2 bar, x3 bar, x4 bar, similarly sigma x1, and so on. Okay. चलिए next. So one-dimensional linear precision measures, which we call it precision indexes, which we have, I think there is no need to revise it again. We all know what we are asking, but it is one-dimensional. Please remember, we are talking about one-dimensional linear precision. So this is the very good table which is prepared. I'll try and see whether you all could, is it visible at your end or not. I'm just zooming up a bit so that let's see whether it is just can Velishetty, is it visible now at your end?
Visible, sir. It's sir.
Okay, good. So on the left hand side you have a bell-shaped function for single dimension, and at the middle, at the center, around mean, you have single set of observation linearly falling in x direction with the ordinate or fx value as the probability, and individual probability you can solve it from standard normal distribution function. We have solved that the 50% probable error would be 0.6745, average error which is considered as 57.51, although the bold one which is mentioned by bold is actually your so-called popular one which is used in our Geo-Informatics, that is 1 sigma error, standard error, map accuracy standard, E95, E99. So these all you have computed. In fact, this table you have computed. This statement you have done in the last class. This is just way of representing of the questions which are generally being asked by in many examination, many interviews. People will ask you what are the representation of 1D errors, and you will probably call these by names. That standard error is one representation, map accuracy standard is one expression, which we call it as a E90 error, E95, E99, and in fact up to 4 sigma. But believe me, as I've told you, that 3.29 sigma is one such threshold which initially was adopted as to detect the outliers, or any observation beyond mu plus minus 3.29 sigma would be considered as outlier. That means if this is your bell-shaped curve and this is mu, from this side we call it mu plus 3.29, sorry, and on this side you will have -1. Okay, but nowadays there is no such threshold, and in fact researchers have declined to accept any such threshold, and they have reason to do so. So but they just mentioned that we have to choose some I mean good robust threshold for deciding this parameter. But anyways, this formula is nothing but it is a formula which you are doing in your exercises, the same formula, the integral way of representing the px dx between a and b. Okay, so all this I think you have done. It's good that you are practicing it, and many of you have submitted it. Those who have not submitted, I mean it's not good practice. You should be sincere enough to submit the assignment on time. There is another assignment, matrix algebra, that you should do. Okay, so another this is the threshold of GPS standard positioning service point accuracy, because obviously this is the basic. Every time you switch in your technologies, the basics of accuracy and precision cannot change. It has to be adopted and the way you are representing errors, every technology has to adopt it. And that is a one way, very good way that you stick to your basic in terms of understanding it. There is one example is given as generally in your GPS, you get the northing, easting, and up component because that has a that the instrument has I mean the field software has inbuilt map projection associated with your data collection. The moment you get the XYZ will be converted to northing, easting, and up component of your projected area, and the errors in meters or the nominal SPS point positioning accuracy is represented as sigma E sigma n by 4 meter, and correspondingly double the error in the vertical GPS. In theories in next semester you will probably learn that the horizontal errors are half from vertical errors, and vertical errors are generally 2 times the horizontal errors. So you could probably see that the relation between the 2 times here, and here. Okay, so these are just way of representing the observation. Okay. Any questions? I hope you have gone through the content as and you are following this very much about the deviations, about the precision measures which we are doing. So I guess it's very much clear to all of you. Then you have relative precision. Relative precision, as I've told you, refers to a ratio of precision of a given measurement to the value of measurement itself. Just like if you have a d as a measured distance, then sigma d is the standard deviation associated with it. Then sigma d by d is called as the relative precision. Okay, and it is the dimensionless and often expressed as the fractional ratio, as by 1 is to 10,000 or 1 is to 50,000 or parts per million, and frequently used with the EDM. In fact, with the GPS, with the total station, it is frequently used. How it is written? Let me tell you. It is written as so. This BPPM is a variable quantity that goes with the DI or SI as the distance, or as long as you're increasing the distance between 2 points, the overall error would change. This A is called as fixed and B is variable, and this variable would be converted to mm when it is multiplied by distance, which is in kilometer. Okay, so I think it is very clear. When we'll go into the next semester, and probably in the theoretical, in the laboratory class, you will probably learn this about the fixed nature and variable nature. Okay. Now what we are doing, we are extending this normal PDF to n dimension, and this is what I mean, we have discussed in the previous class also, that this is the way you represent the 2-dimension case or n-dimension case of your observation, where x is a vector which isn't a single variable, it is a set of n-dimensional variable. So x, for x, which is an n-dimensional random variable, you have mu x which is representing as the mean of random variables. Okay, so correspondingly, we have the sigma x inverse, which is representing the variance covariance matrix. And when you have n-dimensional so-called n-dimension observation, I think just a minute. So n-dimension observation, then it is represented by VCV, which is nothing but the sigma x. This is another derivation which is given for the case of joint distribution, because now you do not have to work with single dimension. That means the picture is not very straightforward like this. The picture is not straightforward like this. Instead, you place your hanky or a napkin on a floor, on a table, and you pick that hanky or your napkin by central point, and you just raise it to a height, and you will see that it is a two-dimensional or three-dimensional figure that is in front of you. You could experiment it right in your friend. You just place a piece of cloth and you just pick it up from center, and from all side it would look like a bell-shaped curve, but it is in fact in 3 dimensions, isn't it? That is what, when we are working with the n-dimension problem, that is what we are looking at. But in the case of linear one, this is the way you can represent it. But in the 3-dimensional, you have to represent it in a specific manner. Okay. So for 2-dimensional case with random variable x and y, this is how you can write. It's very simple way of writing. We are very much, I'm very much sure that you are all following 1 upon sigma root. In fact, this is you will remember the moment you will write 2, 3, 4 times, you will remember it, that fx is nothing but 1 upon sigma root 2 pi exponential minus 1 by 2x minus mu upon sigma square. That's how you will remember it, because I have written too many times and you are also writing it too many times. Okay. This is the joint PDF. We are not going into the derivation part, but it's very straightforward. On any book on statistics, you will just pick it up, or in fact, you just Google it, derivation of a joint PDF, joint bell-shaped PDF, and you could get it. Okay, so we are not going into this, but there is one more application which is we are following here. That's rho. The term is called as rho, which is correlation coefficient. Correlation coefficient will only appear when we are trying to find out the correlation value between two random variables. And obviously, it is represented by sigma xy, that is covariance divided by variances, or standard deviation, I would say. Okay. Anyways, if this mod of any two random variables could be negatively correlated as well as the positively correlated. That's why we have chosen this word mod rho, because this index would have a negative value as well as positive values. Okay, so sigma xy bar would be less than, I mean, this is a very basic mathematics which we have done in your JEE preparation, which you can follow at any time. This is the two-dimensional 2 cross 2 variance covariance matrix between x and y, because here in this picture only x and y are the variables, random variables, and very straightforward. You can write, suppose if I'm new, just like you, how would I write? How would I practice the sigma 2 cross 2? I have to write. Okay, what are x and y? Okay, so if it is x and y, 2 cross 2 I have to write. So first I'll write the diagonal element, sigma x square, sigma y square. It's very straightforward. On the diagonal, you will have variances. On the non-diagonal term, you will have sigma xy, sigma yx. Okay, so sigma xy, if you have to write it, you will write rho sigma x, sigma y. So because sometimes you do not have directly access to sigma xy, instead you will have access to the correlation value, or the correlation between two observation xy, or two random variable xy, and then you can use their individual standard deviation, and you can go ahead with writing sigma xy. Okay, so for normally distributed variables, zero correlation implies independence. It is not true for for other variables not having bell-shaped distribution. It is only applicable for your bell-shaped curve. So normally distributed variable, zero correlation implies independence. But in the other cases, for example, the observables or random variables are not following bell-shaped curve, zero correlation doesn't implies as the independence. But in this case, this is the beauty, or you could also call it as the characteristics of your what should I say, the bell-shaped curve, that this implies zero correlation implies as an independence, and the moment you call it zero correlation, the event or the random variable are independent to each other, the probability combined probability would be given as the multiplication of the two individual probability, which is very fairly known. You have done it and you have seen in the previous class also. Okay, so I hope there would be no more question. See, this is how I wanted you to take a look. I don't know whether it is clearly visible on your screen or not. If it is a problem, just let me know. I'll just do one more, Yes. So the top two equations are representing the random variables, obviously in the two dimension x and y, and distribution is referred to as a two-dimensional normal. And you could see here, this is the way you represent it, x and y. Okay. And if it is B is centered somewhere, not at the origin, but because every time you could see in your basic coordinate geometry, I guess in 10th or maybe 11th, I would say. In 11th, I guess. Yes. In 11th, you have seen that circle is not at origin 0, 0. Instead, it is origined as a comma b. So you'll write equation as x minus a square plus y minus b square is like that, isn't it? In fact, in your ellipse cases also. So similarly here, your the ellipsoid is centered at 0. Sorry, this bell-shaped curve is centered at 0, 0. Here it is slightly deviated. My question, when this would happen, that deviation would occur, chances of deviation would occur. Any possible explanation? Any guesses? अभिजीत बताइए. One could simply say that A would be a case of random errors and B would be case of observables, raw observables, because raw observable would have a mean as well as variances. So this is example of mu as well as sigma square, but this is an example of 0, sigma square. So obviously this would represent the random errors distribution, and this would represent the variable distribution because it would have a different mean, all such. Okay, so the shape of fxy looks like a bell sitting on the xy plane, and whose highest point is nothing but mu x mu y, because that two coordinates are x y, and this is your z dimension, or you could call it fx dimension, the value at top, this one. So these top value is defined by this. I hope it is clear. So now here comes three different possibilities of what we are doing. Planes. So one, here we are presenting it as in if it is call it as fx plane. This is your fxy plane. So when you are projecting it on certain planes, you would be going or converting from 2-dimension to 1-dimension to try to see how the behavior is in linear direction. There would be a possible case that you would doing so. And second is when you try to intersect this uh, this bell-shaped curve with planes at multiple levels. So what we are doing, we are just intersecting these by planes. Just do it the intersection part. You just intersect it from here, from here, from here, and when you see the picture from bottom, it would be a ellipsoid, or it would be a ellipse considering the 2-dimension, obviously. So if when the moment you have such scenario, so obviously it is very much clear that when a plane parallel to xy coordinate plane cuts the bivariate density surface in an ellipse whose equation can be derived by setting fxy is equal to h, or h is equal to k square, a constant which is equal to the height of intersecting plane above xy plane. Okay, so if you are intersecting at this height h, we are talking about that. And when you see the bottom, the moment you cut it and you trying to see from bottom, you will represent an ellipse. Okay, so that's that way we are representing it. So when we are trying to see whether fxy is equal to h, or a particular value h, which we also representing it by k square, how we are going to change, and what would be the scenario that would be represented in next slide. So this is again, you are replacing it or opening up, try to find out the equation. So the derivation you can go through. There is not much difficulty, just you have to follow the content. So what we are trying to reach to a value where we can answer those questions which are imposed in terms of a bivariate distribution, in terms of its error sources or error distribution. What will be the one sigma error? What will be the correspondingly 2-dimensional representative of standard error? Okay, just like we have done in the linear case, we have to also find out the or we have to also give the statement about 50% probable error. In 2-dimensional case, 67.5% probable error, 1 sigma error. What is 2 sigma error? So that's how what we have done in the case of single dimension, we have to again represent in the 2-dimension also. So a joint PDF, which is a joint PDF for bivariate normal, can be written as fx y xy, the first factor, which is 1 upon sigma root 2 pi exponential, the way we are writing, and the second one, which is multiplied by 1 upon sigma root 2 pi, and the whole equation, which is explained previously also. First factor on the right hand side of equation is the PDF of x. The second factor is the PDF of dx. Okay, therefore the integration with respect to y produces the marginal n mu x sigma x square distribution, which of course integrals to 1. And these are the very basic understanding, where your x is represented by n mu x sigma x square, and y would be also represented as, because when you project it, the moment you project the actual distribution on x side as well as on y side, the distribution will be given by the same. However, the for this particular case, we are writing this one. The double integral minus infinity to infinity fxy xy dxy dy dx dy is equal to 1. The integral represents the whole probability scenario, inside this curve. And the correspondingly the condition distribution for bivariate normal distribution, we are representing y by x, that is x n bx sigma y square root 1 minus rho square, where bx is this, and by symmetry similarly representing x by y is as y representing as the normal distribution for by sigma x 1 minus sigma square. So these are the ways you can represent the conditional probability density function of bivariate normal distribution for three different cases. For x is equal to 5, 10, x is equal to 10, x is equal to 15. How the normal distribution curve will be represented in y. So that's how you could do it. Many times these questions are not asked, but you should be aware of it. Similarly, the graphical representation of 2D normal distribution function shows that its intersection with any vertical plane y is equal to ax plus b will be a 1D Gauss normal distribution function. Any plane parallel to xy plane and cutting the bell-shaped surface intersect in an elliptical curve, and obviously conditional density function of y given x can be considered as that of 1D normal distribution. So that means y given x. So we have to find out the probability distribution subject to a given x, and the moment we have a given x, that means for a given x we have to implement or convert this density function. So we will convert for bx and sigma square, just like that we have done in the previous slide. So that would be represented by this figure. You could see this figure from your left hand side. This is the representation in in y, and in this is the representation in z, because x and y both are individual random variable. Okay, this is the two-dimensional case, and in one-dimensional case you could also see that it would be represented by 1D Gauss. So in the 2D case, it would be an ellipse. Okay, intersection plane one. So mean or expectation of conditional distribution of y for a given values of x is a linear function of x, and this function bx is called regression line of y on x. Okay, so the way you are representing these function for a given values of x will be decided by this. Okay, coming back to those curves, which is obviously the case of finding out the ellipse equation, so that we could answer it probably further. The probability of density function fxy can also be geometrically interpreted by intersection of surface xy by horizontal plane fxyh, which is a constant, and resulting curves of intersection lines from a family of ellipse, because sigma 1 greater than 0, sigma 2 greater than 0, and rho between -1 and 1, because obviously we know that the standard deviation is a positive square root. That's why they are greater than 0, and we can replace this by a family of what should I say, the ellipse. Okay, for error analysis in our Geo-Informatics, the bivariate, trivariate normal distribution in general model for the random error components. Okay, we can also move from shifting the origin to 0. So in 2D case, we can shift by origin of coordinate system such that mu x and mu y is equal to 0, and the above equation reduces to this particular value. Why we are reducing to mu x and mu y is equal to 0? The possibility is only that we are trying to find out the 2D error case, if we have to convert it into the 2D error case. So this is the standard equation which we have to follow, that x minus mu upon sigma x square plus y minus mu y upon sigma y square, and then 2 sigma correspondingly x. You could also see that this is a z1 square, zx square you could also call it, plus zy square minus 2 rho zx zy. That's how you can also try to see when we are converting the individual variables to standard normal distribution. Okay. So that's how you see in the case of the representation of error of the planes, the moment plane cuts the ellipsoid, and you could see in the bottom, if the sigma x is equal to sigma y, then this is a case where you will see perfect circular. But in any case, if sigma x is equal to sigma y, and that case is that there is a correlation, or there is a correlation value between these two, that then the change of ellipsoid will take place in this direction. Okay. Similarly, this is the case where both sigma x and sigma y are same. So that means the so-called major axis and minor axis of this ellipse is same. There is another case where you have sigma x greater than sigma y. Then this is the case of negative correlation. This is the case where sigma x is less than sigma y, and this is the case where probably you have another scenario. So I think with this I will stop here. That slide ends at the how you are representing the so-called the error shapes, and when it will be useful. You need to understand first question, why we are trying to see the 2D cases. Why not single cases would be suffice, but we have to see from examples that in order to understand certain observable, we need to understand the 2D cases. And second important point is how the 2D errors are represented. Just like we have represented 1D errors, how the 2D errors are represented. Not only the 2D representation, but also the single variable representation of 2D errors. That means, suppose if we are representing two errors, just like we have done in the case of root mean square, where you have two variables, bias as well as a random error component, and you have explained it that it would be represented by two-dimensional error, root mean square error. But the two-dimensional representation, how it would look like at the second point, what will be the appropriate single dimensional representative of the two-dimensional error. I mean, right now it would be a little difficult to speculate, but there would be correspondingly or equivalent one-dimensional representative of these errors. Okay, we will see that part also. So the equation which represents the size, shape, and orientation of standard ellipse by sigma x, sigma y, and rho. We will try to see how these orientation, and in fact your matrix comes play here also, and the eigenvalue decomposition kind of problems will also see. Okay, so various size, shapes, and orientation of ellipses represent something in our Geo-Informatics. What are these? We will discuss that also. And suppose just by conceptual understanding, people are giving the standard ellipse to you or the ellipse to you and asking the questions from that ellipse, what you can tell about the data set. At that, you could also explain to them. And for k is equal to 1, it represents the standard ellipse. So this the value of k, which is you are putting as 1, would be the case for standard ellipse, just like standard error is 1 sigma error. Okay, in the previous linear dimensional case, you have standard error as 1 sigma. Here the case of 1, k is equal to 1, is representing as standard ellipse. The moment you have ellipse, obviously you can recall in the case of 3D, it would be sphere, isn't it? In case of 3D, we are moving from ellipsoid or ellipse to sphere. That would be also good, nice to see what will be there. Okay, anyways, we'll